This is section 12.5, and we're going to start with a warm-up. So suppose we have this three-dimensional region that's bounded by y equals x squared, and then the planes z equals 0 and y plus z equals 4. I want you to set up double integrals to find the volume using either dy dx for part I or dx dy for part II. So go ahead and put this on pause. Take a second and see if you can set it up. You don't actually have to evaluate. We're just going to do the setup. Okay, in either of these cases, you're going to need to have a really good picture in your head of what this region looks like. So even if you feel not so great about your ability to graph it, we at least, let's talk through how you could at least visualize it. So plane z equals 0, that's probably the easiest one. That's just my xy plane. So that's going to be a boundary. And then the plane z or y plus z equals 4. Typically what I like to do is sketch that. And one way we can visualize it, let's just sketch one trace of it first, and then we'll get the whole thing. So let's just sketch the trace in the zy plane. In the zy plane, it's just going to be this line that starts here at 4 and ends down here at 4. So that's just the trace there. Now this plane continues on, right, for all different values of z and y. I'm trying to show kind of the dimensions there. But right now, let's not worry about that piece as much because we know that that's the top part that's bounding this. Maybe it's a little bit easier to see. But yeah, that's probably a better way to see what it's doing, right? It keeps, if we have the xy plane as a boundary, then this plane is going to just keep going. And we're going to you'll get a lot better at visualizing this through time. But right now, just imagine this is like the top, just the top part of that, or just the plane in the, above the xy plane. And then we're going to think about how we add in this surface. So let's draw that surface separately for a minute, and then we're going to add it onto ours. We'll put it all together. So this surface, if we just draw the trace in the xy plane, this is just going to be a parabola. And so because this doesn't have any z value in it, it's got to be the same parabola for all z. I'm just going to draw it for positive z because we know that we're bounded by the xy plane. Okay, so we now need to visualize how we put these two together, where you have this region that's coming up, but then it's getting bounded by this plane. So I'm going to down below do my best attempt. And what I find is usually easiest is to draw the traces, like what exists in the trace. So in the xy plane, it's easiest just to draw this y equals x squared trace. And then in the zy plane, we can draw this trace. Let's do it like that. 4, 4. And then we're going to try to connect them. This might be a little bit hard to do. You just want to kind of imagine. Here, I'll do it like this. What would happen if you were trying to put these two pictures together? And actually, the way I have that angle there, it's kind of even hard to see the front. I'm going to show you in 3D. And this is where CalcPlot3D or GeoGebra is your friend. You can definitely plot these using online tools. I would just really practice visualizing them yourself in your head because on exams, you won't have the ability to plot these using online tools. Okay, so let's go visual or look at what this looks like. Okay, and for here, just look at the picture. You can ignore the integral right now that's set up there. That's triple integral, which we're going to get to today, but we're going to think about how to set up this volume just using a double integral. So this is what I was trying to sketch, and you can see there's the plane that's coming down here. And then you can see that, oh, it's kind of hard to, there we go, that the shadow on the xy plane is just going to be this parabola. Okay, so let's figure out how we could set up our bounds, given that this is our region. Okay, and for those of you where you had no idea what the picture looked like, I would say, again, put it on pause if this is where you were stuck, and see now, given the picture, if you could figure out the double integrals to find the volume. Okay, so recall to find the volume, if this is the top of my region, this is given by z is equal to 4 minus y, then the volume is going to be the double integral over my region of that height, so of 4 minus y dA. And now the question is, how do we set this up with different bounds? So what we need to sketch is our region of integration, which in this case is just coming from this parabola. This is just looking in the xy plane. This is my region R. So that's also this little region right there. Okay, so let's imagine, oh, first of all, we should figure out where this occurs. So we need to figure out where this plane, z equals 4 minus y, intersects the xy plane, because that's where, that's going to give us the largest y value we can have. And so z equals 0. Note, z equals 0 implies y is equal to 4. So that's going to give us this top part right there. And that means we know these bounds here are going to be 2 and -2, because this is the curve y is equal to x squared. All right, so let's take this. We're going to copy it twice, this region, because we're going to need to imagine slicing it up 2 different ways. Paste over here, depending on which way we're going to integrate first. So if we want to use dy dx, here's what we're visualizing. Set up this integral. Okay, so we're visualizing that we're going to start with this inside integral. And what this means is I'm holding x constant, and I imagine that I am slicing this region parallel to the y-axis. And I would like to look at where that arrow would enter and exit my region, because those are going to give me the bounds that will determine where I start and stop my y integral. In this case, I can see it enters when y is equal to x squared, and it exits when y is equal to 4. And I want us to visualize just that piece. Here, let's go back to that picture. Okay, so if we go back here, one way we can visualize that is for a given x, I'm shooting the arrow. So this is like the idea of the arrow. And then that inside integral is literally going to give me this area of this blue triangle in this case. And I want to add that up now times a tiny little width dx, because I want to find the total volume. So I'm going to take that inside integral, which is the area, and then I'm going to be multiplying by tiny little widths dx in between each of these. And I'm going to add those up in x. And you can see where I add that up in x, I'm always going to be starting my slice at -2 and ending my slice at +2. And so my outside limits are always going to be constants. They're going to be the largest and smallest x values where I could make one of these slices. The inside integral is literally giving me the area of one of these slices. And you can see that the bounds down here depend on x, depends on where we slice. Like this integral right here has much smaller bounds than if I do the slice right here, where it has a much larger bound. So let's go back and work on this. So let's sketch that here. If I make a slice right here, then I end up, this inside integral is finding the area underneath my curve of just that slice. And then I'm multiplying, so this is area of the slice. I'm multiplying by a tiny little width of slice, so that I can imagine getting the entire volume of this region. And I'm adding that up where between x is equal to -2 and 2. Okay, as a reminder, your outside limits will always be constants. They're just the largest and the smallest x values where you could even make a slice. And then that's it. We can evaluate this. And so before we evaluate it, let's practice setting it up the other way. And then we'll just jump to the evaluation. Okay, so let's now imagine that we wanted to slice the other way. And so on my picture up here, instead of slicing parallel to the y-axis, I'm now going to take my knife and slice parallel to the x-axis and look at where it enters and where it exits. And I think I can draw that there so you can see. Yep. Good. That's like my little slice. And then I have to see what my cross sections are going to look like in this case. Okay. And here, okay, so here notice my integrand is the same because that's just the height of the bread and that's not changing either way. Depending on how I slice, that's still just 4 minus y. But now I want to look at where my knife is going to enter and exit. And so it's entering here along the curve y is equal to x squared. And so I need to solve that for x. So that tells me that x is plus or minus square root of y. And so my lower limit, or my left limit, just coming from where I enter the curve on the left, is negative square root of y. And my upper limit is positive square root of y. And then I imagine all the places that I could slice this and think of what's the smallest y value and the largest y value where I could make a slice. And the smallest one is going to be 0 and the largest one is going to be 4. So either of these are equivalent. Either way, we're going to get the volume. At the end of the day, once you do the integral, and I don't think really either one's much easier. One's much easier than the other. This is just a bunch of algebra. There's no like tricky integration technique. But when you do the final integral, you should get okay, so if you finish it, there's just some algebra, but it ends up giving us 256/15, which is going to be the volume of the original region up here. Okay, so that's great. And what we'd like to think about, though, is what if I gave you the density? What if I said that the density was varying at different points on this object, and I wanted to know the total mass? And now we're going to be stuck because I'm not going to be able to do just a double integral to figure out the total mass of this three-dimensional region. In fact, we're going to need a triple integral. So we're going to go on to how we can integrate over three-dimensional regions, chopping them up, and this will lead us to triple integrals.